You've got a mind-bending cosmic puzzle in your hands, and today we're turning it into a dynamic, commentary-driven YouTube script that feels like a creator thinking out loud. I'm not just recounting the science, I'm tearing apart the ideas, the hype, and the implications, while weaving in bold opinions and fresh interpretations. Let's dive in. I'm kicking off with a provocative question. What does it mean when a signal from 8 billion light-years away arrives as a razor-sharp line in the data, and we're told it could be a gigamaser brighter than anything we've seen before? Personally, I think this isn't just an astronomy nerd's dream. It's a storytelling moment about how the universe can magnify its own signals in the most improbable ways. What makes this really interesting is not just the discovery itself, but the combination of a violent galaxy merger, a hydroxyl-driven amplification mechanism, and a fortunate alignment that makes Earth's telescopes a cosmic stage for a brief, spectacular laser-like beacon. If you take a step back and think about it, we're essentially catching a natural laser in space, amplified by gravity, stretched across the history of the cosmos. From my perspective, that's as close as science gets to a real sci-fi prompt becoming testable reality. The hook here is simple. A narrow 18-centimeter line that should have faded into the background instead stayed sharp enough to measure after traveling for billions of years. What many people don't realize is that the 18 centimeters wavelength is a telltale signature of hydroxyl, a molecule abundant in gas clouds. This detail matters because it points to a specific physical process, maser amplification, rather than a random spike in the data. In my opinion, that specificity changes how we view distant galaxies. They are not just islands of stars but laboratories where molecular physics plays out on colossal scales. A detail I find fascinating is how a foreground galaxy acts like a cosmic lens, boosting the signal without creating new light. This raises a deeper question: how often do such lucky alignments occur, and what hidden population of gigamasers could be lurking just beyond the edge of our current surveys? Let's map the core ideas, one by one, with the kind of commentary I'd want to hear in a long-form breakdown. Idea 1. The megamaser signal at Z is almost equal to 1.027. What it is? A hydroxyl maser that's far brighter than typical galactic masers, detected at a redshift of about 1.027, meaning the photons started their journey when the universe was much younger. Personally, I think this situates the finding as a milestone in exploring the distant, gas-rich era of galaxy evolution. What makes this really interesting is that a line so bright survives cosmic distances without blurring. That suggests extreme pumping conditions and a peculiar geometry of the emitting region. In my view, this signals that the interplay between starburst activity and molecular gas can produce extraordinarily efficient amplification, even across billions of light-years. A takeaway: this isn't just more distant radio, it's a window into the physics of extreme environments in the early universe. This matters because it reframes how we search for rare, luminous molecular phenomena in deep surveys and how we interpret their brightness in the presence of lensing. Idea 2. The 18-centimeter OH line as a diagnostic. What it is? The 1667 and 1665 MHz hydroxyl lines are classic maser tracers, and their prominent presence at this distance implies special gas conditions. My take: the emphasis on the line strength, not just detection, elevates this from a casual find to a diagnostic of the gas density, turbulence, and pumping mechanism in a merger-driven environment. What makes this really interesting is the way a molecular clock tells a story about how quickly gas can be converted into stars under extreme compression. In my opinion, the result hints at a broader trend. In the cosmic past, mergers may have crafted pockets of unusually efficient molecular amplification, which could bias our detections towards specific, turbulent phases of galaxy evolution. From a broader lens, this connects to how stellar feedback, gas inflows, and gravitational interactions sculpt the molecular landscape of galaxies on grand scales. Idea 3. The merger-driven pumping mechanism. What it is? A violent galaxy merger concentrates gas, increases density and temperature, and creates the right conditions to pump hydroxyl molecules into states that amplify radio emission. What I'd highlight, mergers aren't just spectacular visually, they are engines that restructure a galaxy's microphysics. This matters because it explains why the signal is so bright and why it's localized to a rare but crucial phase in galaxy evolution. My interpretation, the Gigamaser label is as much about environment as about intrinsic luminosity. If a background source weren't pumped to such extremes, you'd never see it so clearly. The broader implication is that the most dramatic signals in the radio sky may come from these transient, chaotic phases, suggesting a targeted search strategy during non-merger episodes could yield a treasure trove of extreme masers. Idea 4. Gravitational lensing as a brightness booster. What it is, a foreground galaxy acts as a natural lens, boosting the observed brightness and shaping the apparent structure of the background source. In my view, this foreground lens is both a help and a caveat. It lets us see something incredibly distant, but it also muddies the intrinsic brightness with lensing magnification. What matters here is the reminder that cosmic alignment matters as much as intrinsic power. If you're chasing faint, distant phenomena, gravitational lensing effectively lowers the detection barrier, but it also complicates interpretations of true luminosity and size. This ties into a bigger trend, the era of gravitational lensing as a primary discovery tool in radio astronomy, revealing populations we'd otherwise miss and forcing careful delensing analyses to recover intrinsic properties. Idea 5. The efficiency of MeerKAT and what it suggests for future surveys. What it is, the detection was achieved in a relatively short observing window with a large, coordinated array, underscoring MeerKAT's capability for wide surveys and rapid discovery. My take, this is a proof-of-concept moment for next-generation instruments. What makes this interesting is not just a single discovery but the demonstration that bright, distant hydroxyl systems can be found without decade-long campaigns. In my opinion, the implication is that upcoming telescopes, like deeper, more sensitive arrays, could systematically uncover a hidden population of hydroxyl megamasers across cosmic time. The broader connection is to survey strategy. If we design pipelines to hunt for narrow-line, high-contrast features in massive data streams, we might flip the discovery rate of rare, extreme masers from once-in-a-lifetime to routine. Idea 6. The multilayer gas view hinted by HI absorption. What it is, the spectrum also shows neutral hydrogen absorption, implying layered gas with both atomic and molecular components. This matters because it paints a more complete picture of the merger's interstellar medium. My interpretation, the presence of HI absorption alongside OH emission suggests a complex, stratified environment, dense molecular pockets embedded in a reservoir of atomic gas. This aligns with a growing understanding that the ISM in merging systems is a tangled, multi-phase medium. The bigger takeaway is that to understand extreme masers, we need multi-wavelength, multi-phase datasets that reveal how gas cycles between phases during intense star formation bursts. Deeper insight, what this combination reveals about the universe. Taken together, these elements sketch a narrative. Rare, intense mergers craft the microphysics for maser amplification, while gravitational lensing provides a cosmic magnifying glass that makes the signal visible from Earth. What this really suggests is that the universe occasionally hands us these perfect alignment moments where physics, geometry, and timing align to reveal something genuinely extraordinary. From my viewpoint, this is a reminder that discovery in astronomy often comes at the intersection of astrophysics and chance, where the right physical conditions meet the right line of sight. This is also a gentle nudge toward rethinking survey priorities, push for high sensitivity, high resolution, and high-cadence observations in regions with non-merger activity, because that's where the next giant maser could live. Closing thought. If you're watching this and wondering what it all means for humanity's quest to map the cosmos, here's the takeaway: the universe still hides its most dramatic signals in plain sight, waiting for our instruments to catch a lucky break in the cosmic foreground? What would a systematic hunt for gigamasers reveal about galaxy evolution, the distribution of molecular gas in the early universe, or the physics of maser pumping under extreme conditions? My bet is that we are just scratching the surface. So tell me in the comments, would you want a dedicated survey program aimed at finding more gigamasers, or do you prefer the thrill of serendipitous discoveries like this one? Either way, the next chapter could redefine how we listen to the universe's most powerful natural lasers.